Okay, so for the next question, an electron falls 5 cm near the surface of the Earth, right? Considering only gravitational force, how long does the electron take to fall 5 cm? So the Suvat rules, if you apply it, it will just be minus 0.05, right, for the falling 5 cm. So this is assuming I define upward positive for the y direction, and this is equals to this equals to half g, which is minus 10, right? Which, if we define upward to be positive, then gravitational force pulls the thing downwards. So gravitational acceleration is negative because it's a vector pointing downwards, and this will be t squared. And if we solve for t, we actually get the correct answer. But for the sake of being pedagogical, right, I want to show you how this is done using the velocity time graph. So I want to draw a velocity time graph, and because areas of the velocity time graph, it looks nicer if it's positive. So in this case, I'm actually, contrary to the previous convention, right, where this calculation was done using the upward positive direction for y, I'm actually going to, for this velocity time graph calculation, I'm actually going to define y to be downward positive, and that would make my areas positive, areas under the graph positive, which is nicer to work with. So how long does it take for the electron? So it starts from rest and it starts falling. So the velocity starts increasing, right? Downward positive. So as it falls faster and faster downwards, the velocity is increasing. So velocity is positive. And the gradient of this graph we know is 10, right? Because once again, downward positive definition. So given that the gradient is 10, I want to find the time that it covers an area of 5 cm, right? 0.05 in terms of meters. This is meters per second squared. So to do so, we just use the area of a triangle, right? This trapezium, one side is 0, so it's just the area of a triangle. So half times the grade. So the base in this case is just t. The height in this case is just the gradient times the t, so it's 10t equals to the area of the triangle. And we see that if we plug into the calculator, we get 0.1 seconds. Okay, so the answer is A. And we see that over here we've also gotten the same answer if we just applied the formula. But in this case, this is one example where using the Suvat formula is faster. But we can see that I went through the velocity time graph method just for the sake of using the velocity time graph method. But in this case, I admit that the Suvat rules are faster.